We are now on lesson 9.6, Counting Principles. These last two lessons, 9.6 and 9.7, are going to help pave the way for statistics and probability, which is something that's very useful if you're going into a science degree like computer science or engineering or medicine, or even if you're going for something like a business degree. Statistics and probability is a big deal. So these two lessons are going to help give us a basis, a foundation for all of that. So let's pray, and then we'll get into what we need to learn today. Father in heaven, thank you for your kindness and your mercy. Thank you for Jesus Christ and for who he is. Help us to understand the love of God and what the love of God is and what the love of God has done for us. Please bless my student wherever they are today. Give them a blessing, Father, that they may know that you love them, that they may see you and seek your face. I pray that you would help me to explain the material in a way that's understandable, in a way that would be blessing to my student today. We give you praise in Jesus' name. Amen. Okay, let's look at what we want to learn. What should we learn? We want to solve simple counting problems. We want to use the fundamental counting principle to solve counting problems. We want to use permutations to solve problems, and we want to use combinations to solve problems. So let's get right into example 1 first. We're going to look at a situation where we've got numbers placed into two different boxes, one box, but when we draw a number out, we're going to replace that. So 8 pieces of paper are numbered from 1 to 8. One piece of paper is drawn from the box, the number is written down, and then the paper is placed back into the box. Things are shuffled up again, and then the number is drawn back out. The number is recorded on the paper. And then finally, the two numbers from draw 1 and draw 2 are added. How many different ways can we get 12? So, one way to solve this problem is to write down all the possibilities of how you can get 12 from drawing two different numbers. So you could have a 4 and an 8, a 5 and a 7, a 6 and a 6, a 7 and a 5, or an 8 and a 4. And that means that there are 5 different ways to get the number, or to add up the numbers to get 12. Go ahead and pause the video, and I'd like you to try exercise number 11 now. The second example is a lot like the first one, except this time we're not going to replace. So again, 8 pieces of paper are taken and placed in a box. 2 pieces are drawn at the same time, and the numbers on the pieces of paper are written down and then totaled. How many different ways now can we get a sum of 8? Well, there are no repeats available this time. So you can't get a 6 and a 6 at the same time because there's only one 6 in the box. So you can get a 4 and an 8, a 5 and a 7, a 7 and a 5, or an 8 and a 4. And that means there's 4 different ways this can happen. So if you draw at the same time, or if you draw once, replace, and then draw again, that does influence the outcome of possibilities. So the difference between counting problems in examples 1 and 2 can be described by saying that the random selection in example 1 occurs with replacement, whereas the random selection in example 2 occurs without replacement, and that eliminates the possibility of choosing 2 6s. Let's talk about the fundamental counting principle. So examples 1 and 2 describe simple counting problems in which you can list each possible way that an event can occur. When it is possible, this is always the best way to solve a counting problem. However, some events can occur in so many different ways that it's not feasible, it's just not possible to write out the entire list. In such cases, you must rely on formulas and counting principles. The most important of these is called the fundamental counting principle. And here's what it says. Let E1 and E2 be 2 events. The first event, E1, can occur M1 different ways, and After E1 has occurred, E2 can occur in M2 different ways. The number of ways that the two events can occur is the product, M1 times M2. And so this principle can be extended also to 3 or more events. For instance, the number of ways that 3 events, E1, E2, and E3 can occur would be the product of M1 times M2 times N3. So, okay, let's look at an example of this. How many different pairs of letters from the English alphabet are possible? Well, let's just consider the possibility. There are 2 events in this situation. The first event is the choice of the first letter, and the second event is the choice of the second letter. And because the English alphabet contains 26 letters, we can choose from 26 possible letters in the first position, and again 26 possible letters in the second position. We don't mind repeating because there's 2 positions to fill. So that's 26 times 26, which is 676 different possible combination pairs for the alphabet. All right, I want you to pause the video and try exercise 19. Example 4. Let's use this fundamental counting principle. Telephone numbers in the United States currently, as to the writing of this text, have 10 digits. The first 3 are the area code, and the next 7 are the local telephone number. How many different telephone numbers are possible within each area code? Note that at this time, a local telephone number cannot begin with 0 or 1 during the writing of this text. Now, because the first digit of a local telephone number cannot be 0 or 1, there are only 8 choices for the first digit. For each of the other 6 digits, there are 10 choices. And so we have the product of 8 times 6 tens. And that gives us 8 million possibilities. Right now, where I'm recording this is in the state of Maine in the year 2020. And there's about 2 million people in the state of Maine. It's considering based on other states, it's not a very populous state. But there's only one area code for the entire state. And since there are 8 million possible combinations, we only have 2 million people, so that's why there's only one area code for the entire state. You get into very densely populated places like New York, California, Chicago, where there's well more than 8 million people, you're going to have multiple area codes. All right, go ahead and pause the video, and I want you to try exercise number 25. Let's talk about permutations. Whenever you have to put something in an order, first, second, third, fourth, you're talking about a permutation. So one important application of the fundamental counting principle is in determining the number of ways you can take n elements and arrange them in an order. An ordering of n elements is called a permutation. So by definition, a permutation of the n different elements is an ordering of the elements such that one element is first, one is second, one is third, and so on and so on. So let's look at this example. Find the number of permutations of n elements. How many permutations are possible for the letters A, B, C, D, E, and F? Well, for the first position, we can choose any of the 6. But the moment you get to second position, you are assuming that the first position has already been filled. And so now, for second position, there's only 5 letters possible. Again, for third position, you're assuming that the first 2 positions have now been filled, and so there are only 4, and this pattern continues. And so, the possible number of permutations for 6 positions would end up being 6 factorial. 6 for the first, 5 for the second, 4 for the third, and so on. And 6 factorial is 720, which means you can arrange the letters A, B, C, D, E, A, B, C, D, E, and F 720 different ways. All right, go ahead and pause the video and try exercise 39. Here's a powerful formula that can help us calculate the number of permutations of n elements. So if I want to find the number of permutations of n elements, I do the calculation n times n minus 1, continue this product all the way down to 1, but that by definition is n factorial. In other words, if you have n objects, there are n factorial different ways that the n objects or the n elements can be ordered. Counting horse race finishes. 8 horses are running in a race. In how many different ways can these horses come in first, second, and third? There will not be any ties in this assumption. So to get first place, any of the 8 horses could theoretically win. To get second place, you're assuming that the first place position has been open. To get third place, you're assuming that the first and second positions are open. Now there is no fourth place, fifth place, and so on. There are only these 3 places. So you can only have 8 times 7 times 6 possibilities. And so that's 336 different ways you can order the positions of first, second, and third place out of 8 horses. All right, go ahead and pause the video and try exercise 41. Now it is useful on occasion to order a subset, that is a smaller set within the larger set, of a collection of elements rather than the entire collection. For example, you might want to choose an order of R elements out of a collection of N elements. And such an ordering is called a permutation of N elements taken R at a time. So the number of permutations of N elements taken R at a time is this formula right here, NPR, n factorial divided by n minus r factorial. That is starting with n times n minus 1 times n minus 2, all the way down to n minus r plus 1. If I return to the horse problem, we wanted to figure out how many different ways we could get first, second, and third place prizes filled out of 8. That's 8 factorial over 8 minus 3 factorial. So that's 8 factorial over 5 factorial. The 5 factorial divides away, giving me 8 times 7 times 6. Now, it is possible to calculate this on your TI-84 calculator. And so I'd like to try and show you how to do that. Now it's also possible to calculate this on another brand, but the TI-84 is the brand that we have. So we go to the math key, and I hope I'm not wrong, but I believe we need to go over to probability, and there it is right there, second one in the list, NPR. So my calculator has a special feature called math print. So I choose the number 8, I choose the number 3, and I hit enter. And so there's my 336 different ways. Now remember that for permutations, ordering is important. So if you're looking at the possible permutations of letters A, B, C, and D taken 3 at a time, the permutations ABD and BAD are counted as different because the order of the elements is different. Suppose, however, that you're asked to find the possible permutations of letters A, B, and C. The total number of permutations of the 4 letters would be 4p4, which is 4 factorial. However, not all of these arrangements would be distinguishable, and the reason is because there are 2 different letter A's in this list. Swap the A's and you don't really have a new permutation. It's not distinguishable. So now the question is, how do I find distinguishable permutations of ordering? That is, how can I write out all the possible orderings of letters if I have copies of certain letters in the same sequence, or copies of the same element in a sequence, such that the orderings are distinguishable? They're distinguishably different. That's the question. And so this is how we calculate something like that. Suppose that a set of n objects has n1 of one kind, n2 of a second kind, n3 of a third kind, and so on. So let's say I have k different kinds within my set. Then n itself would be the sum of all the numbers of different kinds, n1 plus n2 plus n3 all the way to nk. And the number of distinguishable permutations would be n factorial divided by the product of the various factorials for the different kinds, n1 factorial, n2 factorial, n3 factorial, all the way to nk factorial. So a really good way to see what we're doing here with this formula is to look at this example. In how many different ways, or distinguishable ways, that's the key word here, can the letters in banana be written? So, okay, how many letters does banana have? It has 6 letters. But 3 of those letters are A's, 2 of those letters are N, and there's only one B. And so the first kind is the letter A. That has 3 different ways. So 6 factorial divided by 3 factorial, that comes from the 3 letter A's. 2 factorial, that comes from 2 letter N's. And 1 factorial, that comes from the letter B. Becomes 6 times 5 times 4. The 3 factorial divides away. The final answer is 60. So what that does is that gives me 60 different distinguishable permutations. Now, it doesn't tell me what the permutations are, but at least it tells me how many distinguishable permutations there are. Okay, go ahead and pause the video. I'd like you to try exercise 43. Let's talk combinations. When you count the number of possible permutations of a set of elements, order is important. As a final topic in this section, you will look at a method of selecting subsets of a larger set in which order is not important. So we're now stepping away from permutations. Ordering is not important, just the number of ways we can select. That's what's important. So such subsets are called combinations of n elements taken r at a time. For instance, the combinations ABC and BAC are considered equivalent because both sets contain the same 3 elements and the order listed is not important at all. So you would count only one of the 2 sets. A common example of how a combination occurs is a card game in which the player is free to reorder the cards they have been dealt. So, in how many different ways can 3 letters be chosen from the letters A, B, C, D, and E? The order of the 3 letters is not important. The following subsets represent the different combinations. So in this case, they just wrote them all out. ABC, ABE, ACE, BCD, BDE, ABD, ACD, ADE, BCE, CDE. Those are all the possible combinations. So there are 10 different ways. Pause the video, try exercise 61. All right, let's look at a formula that we'll need if it becomes totally unfeasible to write out all the possibilities. The number of combinations of n elements taken r at a time is the binomial coefficient. We've seen that before. N choose r. N factorial over n minus r factorial times r factorial, which is equivalent to n choose r is also to n permute r divided by r factorial. And so on your calculator, you can find the binomial coefficient by hitting the math key and then by going over to probability And option number 3 is the binomial coefficient. So if I had 8 objects total, how many different ways can I choose 3 objects out of 8 if ordering is not important? 56 different ways. So note that the formula for n choose r is the same one given for the binomial coefficient. To use this formula, or to see how this formula is used, solve the counting problem in example 8. In that problem, you are asked to find the number of combinations of 5 elements taken 3 at a time. So n equals 5 and r equals 3. 5 choose 3 is 5 factorial over 2 factorial times 3 factorial. The 3 factorials divide away. 2 factorial is just 2, so 4 divided by 2 is 2, and 5 times 2 is 10. Counting card hands. Some people have never played with cards before, and that's totally fine. So just really quick, there are 4 different suits in a classic deck of 52 cards. Hearts, diamonds, clovers, and spades, or clubs and spades. 2 of the suits are red, and 2 of the suits are black. And within each list, you have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. A standard poker hand consists of 5 cards dealt from a deck of 52. In how many different poker hands, or the question is, how many different poker hands are possible? After the cards are dealt, the player may reorder them, so order in this case is not important. So we know we do not have a permutation problem, we have a combination problem. So we calculate the binomial coefficient of 52 choose 5. That's 52 factorial over 52 minus 5 factorial times 5 factorial. 52 factorial expanded out, what happens is the 47 factorial divides away, and now we can figure out this combination is 2,598,960. So if you're playing a game of poker and no one's cheating, no one has cards hidden up their sleeves, then there are 2,598,960 different ways you can get 5 cards out of that deck of 52. Alright, go ahead and pause the video and try exercise 63. Example 10, forming a team. You are forming a 12-member swim team from 10 girls and 15 boys. The team must consist of 5 girls and 7 boys. How many different 12-member teams are possible? So okay, now we're dealing from 2 different populations, boys and girls. So there are 10 choose 5 ways of choosing 5 girls, and there are 15 choose 7 ways of choosing 7 boys. So by the fundamental counting principle, there are 10 choose 5 times 15 choose 7 ways of choosing 5 girls and 7 boys. So 10 choose 5 times 15 choose 7 is the following calculation. And so there are 1,621,620 different possible ways that you can choose 5 girls and 7 boys. Go ahead and pause the video, try exercise 71. We're going to conclude this lesson now with asking some questions to help us determine what formulas we need to use to solve which problems. When solving problems involving counting principles, you need to be able to distinguish among the various counting principles in order to determine which is necessary to solve the problem correctly. To do this, ask yourself the following questions. Number 1, is the order of the elements important? If yes, then you're dealing with a permutation. 2, are the chosen elements of a subset of a larger set in which order is not important? If so, then you're dealing with a combination. 3, does the problem involve 2 or more separate events? Well, then you're dealing with the fundamental counting principle if that's the case. And that is the lesson. God bless you wherever you are today.